Hello everyone, I'm Alka Jangir from IIT Kanpur. Today we'll be studying about material selection in engineering design. So this is your course Nature and Properties of Materials, which is offered by Professor Bishak Bhattacharya from Department of Mechanical Engineering in IIT Kanpur. So as always, firstly we'll be going through some sample example questions, then we'll be reading some lecture slides. So first question is, we have to find out the index to be maximized. So firstly, so from first question, we have to find out the index to be maximized to select light and strong material. And in this question, we have to select material for a circular cross-section cantilever beam that is loaded at its end, having high strength and light weight. So your options are sigma square. Sigma is your strength of material, capital E is your elastic modulus, and rho is your density of material. And so this options are sigma square upon E rho and sigma E to the power half divided by rho, or sigma to the power 2/3 divided by rho, or sigma to the power 1/3 divided by rho. So your answer will be C. So we can explain this by this. Now these formulas there will be used. So as we know that we have to select a material which should have high strength and light weight. So density and strength will be compulsorily will be in your answer. So firstly, mass of beam you'll be considering. So mass can be given as density times the volume. So this is your volume of a cylinder. So we know that pi r square h is your volume of cylinder. Here we have written r in terms of d. So pi d square L upon 4. Now mass, we can write d in terms of 32 Fl upon pi sigma. Now this equation comes from your bending, your moment of inertia, and from that will be studying in lecture slides. So from this we'll be getting this formula, then we'll be segregating these in terms of constant, in terms of geometric parameter, and in terms of functional parameter, in terms of material property index. Now in first term you'll be having pi and number constants. In second, L to the power 5 by 3. So geometric will be it can be your length, it can be your radius. In functional parameters, force that we can change, and it can be force, deflection, etc. In material property, these properties won't be depending on the size and shape of material, and they will be constant. For example, materials density and strength and elastic modulus, these are material properties. This index is taken inverse for performance index. So this is what we try to maximize. So we'll be trying to maximizing this performance index, which will be inverse of this unit. So it will be sigma to the power 2/3 divided by rho. So corresponding to this, we'll be drawing lines. So by selecting a particular line above these material, this will be our search region. This is an HB diagram. Now in HB diagrams, what we do, on x-axis we draw certain property, and on y-axis we take another property. Now these are the bubbles that we draw for corresponding materials. So this, for example, these are metals, these are forms, these are some natural materials, these are polymers. So these are drawn, and then we draw these line, and above that, so above that this line will be having higher strength and low density, so this area will be selecting our materials. Now for the second question. So for the second question, your question is which element is most abundant in the atmosphere? Your your options are nitrogen, aluminium, silicon, and oxygen. And it's very easy, so answer will be nitrogen. And we can explain that nitrogen is around 79 weight% in the atmosphere, and it is most abundant. And oxygen is second most abundant element in your second most abundant in atmosphere and most abundant in Earth's crust and ocean. So this is the table. We'll be talking about it later in lecture slides also. And from here we can see that in crust we have oxygen, silicon, aluminium, and iron, these elements in abundance. In oceans we know that water is there, so hydrogen and oxygen will surely be there, and chlorine, sodium will be in NaCl form. In atmosphere we have nitrogen, oxygen is around 19%, argon is 2%, and carbon dioxide is 0.004%. Which of the following strategy cannot be used to encounter the shortage of materials? Your options are batch production, continuous type of product, and effective utilization of machine, or all of the above. Your answer will be batch production. Now batch production is a method of manufacturing where the products are made as specified groups or amounts within a time frame. So these will be some particular part of a assembly will be produced, and another part will be produced differently. So a batch can go through a series of steps in a large manufacturing process to make the final desired product. So this process will be taking more time, so it can't be used for encountering the shortage of materials. In case of continuous type of product and effective utilization of machine, it helps against shortage of materials. Now fourth question is, for a constant growth rate of 5%, what will be the doubling time? Options are 13, 14, 15, and 16. Answer will be 14. And for a constant growth rate R%, R is here 5. The formula for the doubling time is given by TD equal to ln2 divided by growth rate. And when we'll be converting it into log, so it will be log 2 divided by log 1 plus R upon 100. And final formula can be approximated by saying 70 above R. So R we already have 5, so it will be 70 upon 5, which will be 14. So unit of 14 can be, if this growth rate is given, for example 5% per year, then it will be 14 years, or if it is given in hours, then it will be 14 hours, just like that. Now question 5th is, in the design of a fan blade for household application, which mechanical property is least important? The options are elastic modulus of the material, density of material, creep strength of the material or recyclability of the material? Answer will be creep strength of the material. Now we can explain this by saying that for a household fan, the service temperature doesn't increase more than the room temperature. So our fans that we use in our houses, they work at room temperature, and it can increase up to up to 20 degrees, but it won't go as high as 200 degrees C. And this is the temperature that we require for studying creep properties. So creep properties are only required when their temperature increases above 200 degrees C. So creep strength of material won't be necessary. While other properties such as elastic modulus, density of material and recyclability of material, these are important parameters which are considered in designing fan blades. Now McKelvey diagram is associated with, your options are price selection, concept selection, or product marketing, or resource availability. Answer will be resource availability. A McKelvey diagram or McKelvey box is a visual representation used to describe a natural resource such as a mineral or fossil fuel based on the geological certainty of its presence and its economic potential for recovery. So this is what your McKelvey diagram looks like, and the diagram is used to estimate the uncertainty and risk that is associated with the availability of a natural resource. Now, as a geological assurance of a resource's occurrence decreases, the risk will increase. As the economic recoverability of a resource decreases, risk also increases. Now, which of the following strategy cannot be used to encounter the shortage of materials? Options are using recyclable material, following material efficient design, or substitution of rarer materials by an abundant material of almost comparable properties, or increasing the factor of safety. So your answer will be D. And now for increasing the factor of safety, a factor of safety is what? So in certain machinery, if we calculate certain strength of that particular design, so what we do, we find certain uh, area, cross section area, that will give it safety for particular load. So what we do, we sometimes add certain cross section area to that, so we increase its thickness or diameter of the material so that it can withstand up to higher loads. So when we increase it, it leads to the use of more material than required, so it is not helpful in facing the issue of material shortage. While using recyclable materials and following material efficient design, or following material efficient design and substituting rarer material by an abundant material, such as using aluminium instead of copper, these strategies, they help us encounter the shortage of material. Now question 8. Now what will be the index to be maximized for a cantilever beam with a dia D and with deflection delta equal to F L cube upon 3 EI. I is your F is force, L is length of this beam, 3 E is your elastic modulus, I is inertia. Now E is, as I told, elastic modulus, rho is density. So root E upon rho, or E upon root rho, or root rho upon E, or rho upon root E. Your answer will be first. Now this is your cantilever beam. Now we are applying certain force, and this is the deflection that is there, and this is the length of cantilever beam. Now it is of circular cross section, so moment of inertia will be pi d to the power 4 upon 64. Now, and will be taking mass of beam, which is density times the volume. So density is rho and volume will be pi r square h. So in terms of d, it will be pi d square L upon 4. Now we'll be putting value of d square in terms of this formula, and then we find pi by 4 rho L 64 FL cube upon 3 E pi delta to the power half. Now we'll be segregating these properties in terms of a constant, geometric parameter, functional parameter, and material property index. Now these will be constant. This is geometric, so here it will be length, radius, these type of parameters. So it is L times L multiplied by L 3 by 2, and this is functional parameter. So depending on force, your deflection will change. So it is a functional parameter. This is the property which will remain constant for material, and it won't matter what is the shape of your material is. So it is density, elastic modulus. So this is material property index, and we'll be taking its inverse for getting performance index. So this will be root E upon rho. So A will be your answer. Now question number 9. A material is to be selected to be used in the winding of an electrical arc furnace which can withstand temperature up to 1500 degrees Celsius. Now if the desired objective is to minimize cost, and the free variable available is the choice of material, which of the following can't be the constraint for the wire material design problem? Your options are: material should be easily drawn into wire, or material should have high electrical conductivity, or material should possess good resistance to oxidation at high temperature, or material should have high hardness to withstand high temperature. Okay, so your answer will be D. Material should have high hardness to withstand high temperature. So this property is not required, because hardness is not a desirable property if we are trying to wind in form of wire. So winding material, and it does not make it withstand high temperature. Hardness is separate property than high temperature properties. Okay, so other properties that are listed should be considered. So it should be easily drawn into wire, so it should have ductility, it should have good electrical conductivity, and it should have good resistance to oxidation, because it is being worked on 1500 degrees Celsius. Now 10th question is: for a household fan, which of the following mechanical property is most important? Examples are creep resistance, fatigue strength, seawater corrosion resistance, and oxidation resistance. Answer will be fatigue strength. Now we can explain this by saying that for a household fan, the service temperature, it doesn't increase more than room temperature, while creep and oxidation resistance, these properties are required when the temperature increases above 200 degrees C. Seawater corrosion we require when our application is to use it in sea water, near sea water. So for example, your marine applications, they will require sea water corrosion resistance. And fatigue property is the most important, as it is as cyclic loading is involved in fans. Now we'll be going through some lecture slides. So firstly, material selection in engineering design. So mechanical design refers to the mechanical components that have mass, they carry loads and other functionalities such as thermal, electromagnetic requirements, and they must be manufactured. Now design refers to the selection of engineering materials based on set of defined properties. It is a repetitive process. So this is flow chart. So firstly we mark it if we need certain design requirements. So first we come up with a concept. So for that we determine function structure. We seek working principles and we evaluate and select concepts. Then the embodiment of the idea. So we develop layout, scale, form. Then we model and analyze assemblies. Then we evaluate and select layouts. Then we require detailing. So we go for analyzing components in detail. We optimize performance and cost, and final choice of material and process. Then we go for product specification. Then iterate means we repeat these processes until we get a very efficient design for our application. Now selection of properties. So these are certain properties that we need to consider. So price and availability, density, modulus, damping, yield strength, tensile strength, hardness, fracture toughness, fatigue strength, thermal fatigue resistance, creep strength. These are certain mechanical properties that are required. Thermal, optical, magnetic and electrical properties depending on application, and oxidation, corrosion, friction, abrasion and wear resistance, ease of manufacturing, joining, etc., and appearance, texture, feel, etc. Now these properties, they can be divided into certain classes. So classes of property affecting product design. So first class is economic and environmental class. In this, these properties are price and availability, recyclability, sustainability, carbon emissions. So with global warming and this a lot of carbon emission that is related, so nowadays we are very much we give importance to these properties a lot. Second is mechanical. Now mechanical properties are modulus, elastic modulus, yield and tensile strength, hardness, fracture toughness, fatigue strength, creep strength and damping capacity. Other properties are thermal properties. So these properties are required, for example, in boilers and other applications such as heat exchangers. So here thermal conductivity, specific heat, thermal expansion coefficient, these are needed to be considered. General physical properties, density, electrical and magnetic will be consisting, resistivity, dielectric constant and magnetic permeability. Other is environmental interaction. So interaction of a material with environment, it will lead it generally happens through surface. So surface properties will be oxidation resistance, corrosion resistance and wear resistance. Seventh, production properties are how easily we can manufacture certain product from material, how easily it can be joined if it breaks, and how easily we can finish its surface. Aesthetic will be its color, texture and feel. Now we need to determine mechanical properties. So this is one of the example is by using tensile QTS, ultimate tensile testing. So in this we'll be performing the test, then we'll be getting the data, we plot it in terms of stress strain diagrams, then we by analysis we get information on various mechanical properties. So these are the properties that we try to get. Then depending on these properties, we decide what will be the design of material and what potential applications that can be. And based on that, we design the product and we do economic analysis and business case. Now other important aspect is relative prices. So if we try to select certain material for particular application, we have to consider its cost as well. For example, these are the costs that are given. So for example, I'm trying to make wires, so I can also choose aluminium, I can choose gold, I can choose silver, I can choose aluminium. So among these, aluminium is the cheapest, so I'm more likely to go for aluminium than for gold and silver, which are very expensive, which are given here. So for example, here cast iron is always cheaper than steel, so it is we are more likely to use cast iron instead of steels. And these cement, coal, softwoods, these are very cheaper, so we make building structures and roads by using these. Now these are the most expensive things are platinum, diamonds, gold, silver, CFRP, and cheaper ones are mostly polymers and ones that we get from nature such as woods, etc. Abundance of elements. So these are the elements that are abundant. So if certain element is abundant in nature, then it is more likely to be easier to extract and use it in certain applications. For example, if antimony and these type of elements which are hard to obtain, then we are less likely to make it, use it for particular application, and we are more likely to use aluminium, iron, these type of elements. So in case of crust, oxygen, silicon, aluminium, iron, calcium, these are abundant elements. And in case of oceans, oxygen, hydrogen, chlorine, sodium, these we can get from oceans. And from atmosphere, nitrogen gas, oxygen gas, argon, carbon dioxide, these we can get from atmosphere. Now the concept of doubling time. So it is the period of time that is required for a quantity to double in size or value. So when the relative growth rate, not the absolute growth rate, is constant, the quantity undergoes exponential growth and has a constant doubling time or period. Example is applied to population growth, inflation, resource extraction, consumption of goods, compound interest, and the volume of tumors. For a constant growth rate of R%, the formula for the doubling time TD is given by ln 2 upon growth rate. In terms of log, we can write log 2 upon log 1 plus R by 100, and by simply we can say 70 upon R. Resource availability. Now current reserve is the known deposits that can be extracted profitably at today's price using today's technology. So this is the reserve in your McKelvey diagram. So if we are moving downward, then will be having minimum mineable grade. So grade the mineral will be depleted in that particular element, so we'll be requiring to improve our mining technology, and it won't be economic. If we move to this side, then this is the identified ore and will be requiring undiscovered ores. So it will be requiring increased prospecting, and it will be decreasing degree of geological certainty. And if we are going downwards, then it is decreasing degree of economic feasibility. Now these are the certain materials and their energy that is required to them extract it. Aluminium requires a lot of energy, around 280 of the energy, and these plastics are lower compared to aluminium. Copper and the easiest ones are cement, bricks and gravel, so these we use very abundantly. Now another factor is availability. Now copper, silver, tungsten, tin and mercury are rarely available, and iron and aluminium are most widely available materials. Steel consumption is doubling in every 20 years because steel we already using a lot from beginning, so doubling requires higher time. While aluminium and polymer are relatively new, so doubling is in less years. So aluminium consumption is doubling in every 9 years, and its growth is increasing fast for aluminium and polymer. Polymer in every 4 years. Now how to encounter shortage of materials. So these are three ways we can encounter the shortage of materials. So firstly, we can use material efficient design. So if we use and design so such that it uses materials efficiently. For example, if a rare material is there, so it will use rare material to the minimum, while an abundant material, it will use higher quantity of that. Then use less amount of material. For example, for a good surface property, we use cheap substrate and good surface finish. Substitution. Now we can substitute rarer materials by the more available ones. For example, copper can be substituted by aluminium. And recycling, we can use recyclable material like aluminium. So recycling is very popular nowadays because a lot of elements that are used in making mobiles and your smartphones, they are not very abundant in nature, so we need to recycle them. Now these are the examples of some critical minerals that are used in advanced technology. For example, germanium, if it gets depleted or if it becomes extinct, then we are more likely to face problems in making solar panels. So in case of solar panels, arsenic, germanium, indium, tellurium, these are certain elements that are used. In case of battery storage, cobalt, graphite, lithium, manganese. And in case of wind turbines, aluminium, rare earth elements. In national defense, chromium, gallium, scandium. And in case of aviation, niobium, tantalum, vanadium, these elements are used. Now another aspect is eco-efficiency. So it merges both ecological and economic goals. So improving the productivity of energy and material inputs to reduce resource consumption and cut pollution per unit of output. It is a win-win approach that benefits both the bottom line and the environment. Now in 1989, Procter & Gamble introduced concentrated detergent powders, which were called ultra detergents. Now that took up half the volume of traditional detergents and the products cleaned the same amount of clothes but were more convenient for consumers to handle and use 30% fewer raw materials, and they required 30% less packaging and substantially cut the energy needed to transport them to market. Now 7 dimensions. So first dimension is reduce the material intensity of goods and services. Second is reduce the energy intensity of goods and services. Reduce toxic dispersion. Enhance material recyclability. Maximize sustainable use of renewable resources. Extend product durability. Increase the service intensity of goods and services. So if a product's durability also increases, if it can be used for rather than 5 years, if it can be used for 10 years, it will also reduce the burden on the materials. Now greater the improvement in each of these dimensions and more there are the dimensions, the more eco-efficient a product or process will be. Now these are the HP charts, and in these are 2D charts. So on x-axis will be drawing a property, on y-axis will be drawing another property, and these bubble charts will be formed for different type of materials. So metals, ceramics, composites. So these will be giving us an idea. So if I want to use an material for a certain application which requires higher strength and lower density, so I'll be, for example, I require density lesser than 1000 and strength higher than 100, then my search region will be like this. So in this area only I'll be searching for materials. 3D chart. So performance of a component depends on a combination of various properties. So 3D chart here is of Young's modulus, density and strength. So for 3 properties also it can be drawn. Now we'll be taking 4 examples of finding out these performance indexes. So for first example is in cantilever design. So problem statement here will be select a cost effective material for a circular cross section cantilever beam which is loaded at its one end, having high stiffness and lightweight. So stiffness will be in terms of your elastic modulus and lightweight will be in terms of your density rho. So in your final answer you should be having E and rho, and next will be in high strength. So in final answer you should have sigma in your answer. So here firstly solution. So free variables we have radius of circular beam cross section. So we can vary the radius and we can change material. Constraint is maximum deflection and beam length. So we can change length and we can change deflection. So tip deflection is given as delta equal to F L cube upon 3 EI. I is your inertia and E is elastic modulus, F is force, L is length. So the end force and the tip deflection are thus related as F equal to 3 EI upon L cube times deflection. Here 3 EI upon L cube is equivalent stiffness. For circular cross section, I is equal to pi d to the power 4 upon 64. Now combining these formula, firstly we'll be finding out mass of beam. So this beam has the mass, it will be mass of cylinder. So for firstly we'll be multiplying density to the volume, density is rho and volume will be pi r square h, and in terms of d pi d square L upon 4. So we'll be putting value of d by using these two formulas for deflection and I inertia. And d square will be 64f L cube upon 3e pi delta to the power half. So your m will become this, and then we'll be segregating these in terms of constant, geometric parameter, functional parameter and material property index. So your constant will be this and geometric parameter will be L times L to the power 3 by 2. Your functional parameter will become f upon delta in under root, and your material property index will be in terms of rho and E. So these are the properties that won't depend on material shape and size. So rho upon root E. This is your material property index. We have to minimize this thing and we have to maximize performance index. So performance index will be inverse of material property index. So it will be root E upon rho. Now maximization of this performance index gives us the solution. Now we require some kind of cutoff value intercept C. So root E upon rho, for this we'll be taking certain intercept and then we'll be trying to draw a line. Then above this line you'll be finding your suitable material, and below this your material won't be suitable. Taking logarithms on both the sides, we get log E equal to 2 log rho plus 2 log C. We now get a plot of a log plot of the system, that means log E over log rho. Then depending on this cutoff value C, we actually have a straight line in the log plot, and the materials which are below this point are not suitable, and the materials which are above this point, these materials will become suitable for our application. Now this is the example. This is the Ashby chart for Young's modulus versus density. So this is the line corresponding to e to the power half upon rho. So above this line it will be our search region. So we'll be finding the appropriate materials above this line. So we can use these materials, but we can't use elastomers and polymers. Now CFRP is the best material in terms of performance, but it is very expensive, hence wood is the best choice among the given materials. So we are firstly, these are the materials, we are taking their E, rho, and we are calculating this property. Then we see that CFRP has the highest and second highest is wood, and price is the highest for this CFRP and it is very low for woods. So we'll be considering this option. Now second is high strength cantilever design. So it will be similar to previous one, but here we require strength instead of stiffness. So problem statement is select the material for a cross section cantilever beam, circular cross section beam, loaded at its end, having high strength and light weight. Now in the previous slide we found out that the performance index of lightweight and high stiffness beam was root E upon rho. So here we have three variables as beam diameter and material choice, and constraint is maximum deflection and beam length. So these will be constant. We'll be neglecting self weight of the beam, and using bending theory we get sigma equal to md upon 2I. M is your bending moment, which can be given as F times L. F is force, L is length. Now sigma can be rewritten in terms of inertia. So I will be your pi t to the power 4 upon 64, and we can write t as 32 FL upon pi t to the power 1/3. Now mass of beam, again will be always taking this mass of beam, then m will be equal to rho pi d square L upon 4. Similarly to the previous question, here we'll be putting value of d. Now this from there, here we'll be putting this value, then we'll be similarly segregating our constant, geometric parameter, functional parameter and material property index. Now material property index is your here rho upon sigma to the power 2/3, and functional parameter is f up to the power 2/3, and geometric parameter is L to the power 5/3. Now we always try to maximize performance index, which is inverse of material property index. So it will turn out to be sigma to the power 2/3 upon rho. Now because for many safe engineering designs, we can at most take the sigma, particularly if it is linear elastic system, then your tensile strength will be equal to yield stress. Now we try to maximize the performance index, and it gives a solution. We require some kind of a cutoff value, so we'll be keeping it equal to constant, and we'll be taking log on the both sides, and we'll be drawing it on the graph. So this area above this line will be suitable materials, and materials below this line won't be suitable. Now this when we'll be drawing this line in the Ashby diagram, we'll be selecting these materials. So this is our search region. So the intercept of the inclined line is adjustable to suit our needs, but the slope is fixed for a particular performance index. Now third example is connecting rods for high performance engines. What is a connecting rod? So a connecting rod is an engine component that transfers motion from the piston to the crankshaft, and together with the crank they form a simple mechanism that convert reciprocating motion into a rotating motion. So this is what your connecting rods looks like. It has a width and a length, breadth, these all three. So it has a rectangular type of cross section. This is the force that is applied. Now function is connecting rod. Objective is to minimize the mass. Constraint is that we have length is specified. It must not fail by buckling under given force. It must not fail by fatigue under given force. Free variable is we can change cross section area, we can change material. Now first we assume shaft has a rectangular cross section. So A will be this B times W as shown here. Now objective function equation will be m, your mass will be your density times volume. Volume will be area times length. Now the fatigue constraint requires that F upon A. So it is stress. Stress should be lesser than your endurance limit or equal to endurance limit. So here we'll be putting value of this in terms of value of A in terms of this equation will be putting here. So first material index will be getting. So here sigma E is endurance limit, which is stress level below which material will not fail by fatigue for even infinite number of cycles. Now first material index will be rho upon sigma E. So here as I'll be putting value of sigma E, A will be here, so it will be F upon sigma E. So F upon sigma E, so rho upon sigma E will be material index. M2 will be rho upon E to the power half. Now these two material indexes, they can be coupled by this equation. So it is alpha pi square upon 12 F upon L square times the half. Now here this alpha is shape factor and this whole is known as coupling constant. Cc is its symbol, and this F upon L square is also known as structural loading coefficient. Now we draw coupling lines for two values of F upon L square, and we plot by taking alpha as 0.8. Now these are the two lines that we draw for coupling line. FL square equal to 5 MPa and one is for 0.05 MPa. Now at these lines, so first is beryllium. These alloys, they are in middle, so these are best choice for all values of coupling constant within this range. And when FL square is large, so when it is 5 MPa, then we see here, so below in this region it is titanium, 6 aluminium, 4 vanadium alloy. So this is the best choice. If we take this coupling line for 0.05 MPa, then in this area, so this magnesium alloy, which such as AZ61, it offers lighter solutions than aluminium and titanium. Now materials for high performance connecting rods. First is magnesium alloys, AZ61 and related alloys. They offer good all around performance. And titanium alloys, titanium 6, titanium, here it is given 6 aluminium, 4 vanadium is the best choice for high F upon L square value. And beryllium alloys are ultimate choice, but they are difficult to process and very expensive. Aluminium alloys are cheaper than titanium and magnesium, but they have lower performance. Now fourth and last example is design of a probe for scanning probe microscope. Now this is what your scanning probe microscope looks like. In this is a cantilever beam and this is the tip. Now this tip is scanned on this surface. Now it will be scanned in this direction, so this is an surface feature. So this tip will try to deflect because there is this feature. So this deflection is noted by this laser beam and by observing this through this sensor, which is a quadrant photodiode. Now using this sensing, we draw these images in this format. So we get this like at which area there is depth, on which area there is certain surface features. Now this SPM, it forms images of surfaces using a physical probe that scans the specimen by feeling or touching the surface with a mechanical probe. Now the probe is a cantilever beam whose end deflection is detected as a change in the laser beam position at the detector. The bottom surface of the probe has a sharp tip, which is this tip is 3 to 6 micrometer tall pyramid with 15 to 40 nanometer end radius. Now deflection corresponds to surface topography. Now what we are trying to do is we are trying to select a material for cantilever beam such that the resonating frequency is maximized. Now this is your cantilever beam and this is the tip. Now this is the length L, this is width, this is the thickness T, this is the height, so it is the from here to here, it is length of tip. Now our objective is maximization of resonating frequency. Constant is this length is fixed and this thickness is fixed. Free variable is that we can choose material And cantilever should have a high resonant frequency, preferably in the range of 30 to 100 kilohertz. Now, force between the tip and the sample, it leads to a deflection of the cantilever according to Hooke's law. Now firstly we'll be considering frequency we have to maximize, right? So we'll be considering angular frequency omega equal to under root kb upon m effective. Now here kb is stiffness, m effective is effective mass. So end deflection of a cantilever beam is delta, which is F upon L cube upon 3EI, and F upon delta will be equal to, from this equation it will be 3EI upon L cube. This one part is known as stiffness kb. So we'll be putting this value in this equation. Effective mass can be given as 33 upon 140 times the mass of the beam. So mass of beam, this beam we know already that it will be density times the volume. So volume will be length times width times thickness. So LWT, and WT we can get MB upon rho L. Now linear frequency will be 1 upon 2 pi times the kb root kb upon m effective. Now we'll be putting kb value and m effective value, and for that I is w t times 3 d w t to the power 3 divided by 12. So we'll be taking this equation as well, and so the entire equation will be F equal to 1 upon 2 pi times under root 3e times the w t to the power 3 upon 33 upon 140 times the rho L wt times the 12 L cube. Now on solving we'll be getting this equation. Now this part should be maximized because this is the material index. Now we'll be getting material index and then we'll be taking its logarithm part. Now we'll be choosing material with high ratio of elastic modulus upon rho times the half. So the slope will be 45 degree. Now we'll be getting this line and search region will be above this. So these materials, these will be our appropriate materials. In practice, the cantilever is typically made up of silicon nitride, which is here. It's shown here, which is above this, inside this search region, or diamond with a tip radius of curvature of order of nanometers. So this is your Ashby diagram. So in this we'll be drawing this line corresponding to this performance index, and we'll be finding our material, which is silicon nitride. Now that's all. If you have any query, you can ask.
Madam,
Yes.
assignment 7, can you please
Yes.
discuss the assignment 7, question number 5?
Question number 5 in assignment 7.
Yes, sir. Yes, madam.
Let me see.
5 and question number 6, madam. Question number 6.
Assignment given by sir, right?
Yes, yes, madam.
Okay, let me check. Assign question number 6.
Madam,
Lightest cantilever beam of given length L and square cross section does not reflect more than a permissible value delta under its own weight upon rho square. So square section is there, so you have to take area lightest cantilever beam. So it will be similar to this question that is on the screen, but cross section will be circular, so your inertia value will be for circular one, and value of this volume will be also in terms of circular one. What did you take I for this? Uh, Hello.
madam,
Yeah, what did you consider I for this problem?
the square cross section
Yeah, for square one.
a power 4 upon 12.
12. Yeah. By using that, what are you getting answer?
I couldn't understand the under its own weight permissible value delta under its own weight. That statement I have not understood. Does not deflect more than a permissible value delta under its own weight.
In the
That the
question,
statement
in the
some confusion.
question there is statement square cross section does not reflect more than a permissible value delta. So they are trying to say that there is certain limit for that, so it can deflect will above that. And in this case also, I think sir has taught this example. In that also they said that it won't deflect under its own weight. So if you are not applying any force, then it will be in this single line. It won't be like bending to the gravity because of its own weight. Okay, so you don't have to give it any deflection at that particular time when there is no force acting on it. And here also we are taking constant maximum deflection, so deflection is there will be certain permissible deflection. We don't want it to deflect very much, so there should be some stiffness in it. So that is what it's trying to say.
Madam, in your last lecture also,
Yeah.
smart materials, week 6,
Yes.
smart materials. lecture, we
Yes.
have discussed about some problems, sample assignment problems.
Yes.
In the seventh problem, a piezoelectric sheet of length, some value you have given, and you have asked to calculate some uh,
In my lecture or in sir's lecture?
in your lecture, madam. In your lecture
Okay.
only.
In smart.
Question number seven. Question number seven. You have given the explanation also, but some doubt is there.
Okay, in seventh question. Okay, I'll open. In smart materials, right?
Ah, yes, madam.
In seventh question, yes. Share again.
In your lecture.
This one.
Ah, that's, this is the question, madam.
Yes.
Here, what tells about those one, two, three, madam?
1, 2, 3. These are the directions. Like they
Yes.
are defining these constants in these direction like that. So appliance and these D31, these constants, and how they are also telling like electricity is going in this direction and all, for understanding that for that purpose.
What is the meaning of D31, madam?
D31 is your constant that we are trying to multiply it with here. So it has this relation like strain and electric field. In case of piezoelectric materials, this is the constant, piezoelectric constant. So that's why in particular directions it will be different. For example, if we are applying this electricity in different directions, so in different direction it will show different type of strains. Okay, so depending on that it will be having these different type of constants. Like in other example also, here we have D33. One will be showing like it can be, one can be corresponding to one plane, another digit can be corresponding to certain direction, like that D31, D33. So that's what it is telling, like longitudinal piezoelectric constant is for D33. Okay.
Here, value, how much value? Minus 274 into 10 power minus 12 millimeters per volts.
Yeah.
And electric field applied, how much he has given.
Electric field with your operating voltage is given in voltage 1 kilovolt, so you have to multiply it with 1000. Kilo is there, that's why. And this
In the,
well, this
in the explanation, for the question 10, N into D33 into V. Number of usual is 10.
yeah.
D33 is how much? 10 into 10 power minus 12. Okay. Question 10, I have understood. Question 7, please explain me. Question 7.
So 7 in this also, a piezoelectric sheet of length, you have given length, width and thickness. Okay,
Yes,
this
ma'am.
sheet's thickness is along this direction, so you are applying your voltage along this direction, right?
Yes, ma'am.
This much we know. So as shown in figure, and it is subjected to force along the one direction. So force part is here for different question. So force part we won't see here. And other part is voltage is 100 volts is applied to the electrodes. So if there is 100 volt applied, if it is a piezoelectric material, there will be certain strain induced in it. Okay, this part we understand.
Ah, yes, ma'am.
There'll be certain strain.
Hmm.
So these are the constants that we can use. It is given D31, S11, it is given. Now we have to calculate free strain of the sheet in microstrain. Microstrain is nothing but 10 to the power minus 6 is will be multiplication. So we have to remove that part. Now these are the examples. Now this is the simple formula dik when it is written. So it is just this constant is just the ratio of the strain that is induced in I direction. I is first digit. So three direction is in this direction, right? It is given in this direction along thickness. Are you following?
Uh, uh, three direction is I, madam.
Yeah, three direction
Uh,
is I because we are taking D31, right?
uh,
So 3 is I, K is your 1. So along one direction electric field is applied. Electric field will be in one direction.
oh,
Okay. So if D31 we are then for getting strain will be multiplying these two. Okay. So D31 will be multiplying with electric field applied. Now electric field we can write by simply voltage divided by your length. Now length we can see it is in thickness direction. So thickness will be dividing
voltage divided by.
thickness. So length is there. Electric field can be given voltage divided by length. Now voltage is 100 volt and your thickness will be 254 times 10 to the power minus 6. So this is if we remove point and then it will be 254 times the 10 to the power minus 6, right?
Okay, okay.
Now by solve it will be minus D31's value is minus. Okay, keep that in mind. Here it is given minus, so put minus as well. Then after solving we'll be getting 107.87 times 10 to the power minus 6. Now it was shown micro strain, so you have to remove 10 to the power minus 6 part. So minus 107.87 will be your answer.
Length is not used in this length and
Width is not used, no.
not used,
In case of, yeah,
and also and also that value SE11 value also not
yeah,
they have not used.
this was a two part of question, so I've taken one part of this question. In other part they had asked question based on force as well, so in that you will be requiring this formula, this S11. So we have not asked that in that here. So S11 is compliance that is used when we calculate force and for that part. Okay, here we will just require this thickness part because your electric field is applied in this direction along three direction.
For to calculate the force, what is the formula, madam?
For calculating force it will be similar to this. I think I have given in below in piezoelectric materials. One second. Converse effect. I think by using these direct effect and converse effect you can get these. Like compliance is given here as, and D is piezoelectric constant. So by using these also you can get them. But sir didn't ask this question, so I didn't add that question here.
Madam, are you going to end this session?
Yes, you can leave if you want. I'll be present here till 5, but it's ended. I've covered all the slides.
Okay. Next week will be the last live session, I think.
Yes,
Exam also very soon we are having exam.
yeah. When is the exam? 20.
Madam,
When is the exam? Around 24?
uh, hall tickets not generated up to now, madam.
Okay.
As per the schedule, it must be 30th. Whether it is 30th or 29th, hall tickets not released.
Okay, yeah.
Thank you, madam. Anyhow,
Okay, sure, sure.
this will be updated in the Google Drive, madam.
Yeah, I'll update today. After this session, I'll update.
Okay. Thank you, madam. We are
Okay,
leaving this session. Thank
okay,
you very much.
sure, sure.